Welcome back. In this video we're going to explore left-hand limits and right-hand limits. We've been doing this already in our last assignment. We're going to also explore algebraic simplification to find limits. We did that on our last assignment as well. We're going to be using some graphs to find limits. And then finally we're going to incorporate what we call the sandwich theorem. We're going to use this sandwich theorem to develop the concept of the derivative of the sine and the cosine later on in the class. The first thing we have for you is a summary of all the properties of limits that we've been working on. This is a good quick reference for you. You might want to copy these down or print this page so that you have it to refer to. A couple of things that are really helpful. If you just have the limit, remember the limits are y values. So if you have the limit as x approaches an a value of a constant, it's just going to be that constant. If you have the identity, it's just going to be whatever you're approaching. For 3, 4, 5, and 6, it's basically if you have the limit of a polynomial function, you can separate them out individually. If you have a product, you can separate it out individually and then multiply them. If you have the composition, you can take the limit of the inside function and then f of that inside function. I'll do an example of this one. This has been popular on recent exams. If you have a quotient, you can take the limit of each one individually. 7 through 13 are some more like polynomials or pulling constants out front or powers or raising to a power or roots, that kind of thing. The one that's new is number 14, the sandwich theorem. And what the sandwich theorem says is that if you have a function h that falls between f and g for all values or the values that we're looking at, and you might not be able to find the limit as x approaches a of h, but you can find the limit as x approaches a of f and of g, and they converge to the same value, so they both converge to L. Then the limit as x approaches a of h of x has to be L. We're going to do this with sine and cosine, and what you're going to see is that sine and cosine generally fall between -1 and 1 from pre-calculus. And then we can evaluate a limit overall. So in this problem, my first example, I want to find the limit as x approaches 0 of x squared times the sine of 1 over x. We can't evaluate this limit because I cannot put in 0 because I'll get division by 0. I can't algebraically simplify this at all. It's not like I can use any trig functions or anything like that. But what I can do is I can evaluate this. If I were to take and I say, okay, well, the sine of 1 over x has to always fall between -1 and +1. That's true because of our max and our minimum values for pre-calculus from last year. Now, if we were to multiply through by x squared, I can establish this relationship. -x squared has to be less than or equal to x squared times the sine of 1 over x. That's our middle function, which is less than or equal to x squared. And if I take the limit of these outside functions, the limit as x goes to 0 of -x squared is 0. The limit as x goes to 0 of +x squared is 0. Therefore, my conclusion by the sandwich theorem is that the limit as x goes to 0 of x squared sine of 1 over x also must be 0. We use this sandwich theorem stuff a lot with sine and cosine, and we're going to use it to develop the concept of the derivative of sine and cosine a little bit later on in our next unit. The second example I have for you today is this one, which deals with the composition. And I have a couple of graphs. My graph on the left is h. My graph on the right is g. And I want to evaluate the limit as x goes to -1 of h of g of x. So it's composition of a function. From our properties, I can write this as h of the limit as x goes to -1 of g of x. Now, if I look at just the inside part, so if I cover up and I look at just the inside part, the limit as x goes to -1 of g of x, I'm going to focus on this graph right here. So over here at -1, the point's at 2, but the limit is 3. The limit is 3 because as I converge to -1 from the left and from the right on g, I get to 3. So really this says, what is h of 3? h of 3, now I go to my graph on the left, h of 3 is 1. So 1 is my correct answer. I'll try to clarify. This has been a very popular type of problem that they've asked on the AP exam the last couple of years with these graphs and evaluating the limits based upon the graphs. All right, I'll see you in class. Clear up any questions you might have. Get you going on this limit stuff.